At a circus, a human cannonball is shot from a cannon at 15 meters per second at an angle of 40 degrees above horizontal. She leaves the cannon 1 meter off the ground and lands in a net 2 meters off the ground. So she starts 1 meter off the ground. She goes, let's say she's shot this way. So she goes like this and lands 2 meters off the ground over here. But if we look at the change in position, it doesn't really matter that she starts 1 meter off the ground. We can say this is the origin. So she ends 1 meter above where she started. Okay, so let's make this the positive y direction and this the positive x direction. So delta ry is 1 meter. So if r1y is 0, r2y is 1 meter. That's if we put our origin here and say that up is positive. If our origin is here, r1x is 0, t1 is 0, and the human cannonball, if we draw a free body diagram, we have only the force of gravity acting downwards. That's equal to m times g, and by Newton's second law, the net force is equal to the mass times the acceleration. Therefore, if we compare this and this, the acceleration is equal to g, and that's pointing downwards. So the acceleration is in the y direction, negative 9.8 meters per second squared, and the x component is 0. Let's go back and look at the problem statement now. So the human cannonball is shot from a cannon at 15 meters per second at an angle of 40 degrees above horizontal. So if we draw the velocity vector, that's v1, which is equal to 15 meters per second. This is at an angle of 40 degrees, and this is v1x, and this is v1y. v1 is equal to 15 meters per second. And then to find the x component of the velocity, you would do v1 times cosine of 40 degrees. This is v1x. v1y is equal to v1 times sine of 40 degrees. Okay, when we draw our free body diagram, when we draw our vector diagram, we want to use the position kinematic equation, which we have here. We draw a vector for delta r, we have that here. We draw a vector which is pointed in the same direction as the initial velocity, but it's multiplied by delta t, so the length is not the same. The units are not the same. So we draw this vector, it should be at an angle of 40 degrees. This is v1 times delta t, and the angle for this vector is 40 degrees. So we get that from the 15 meters per second at an angle of 40 degrees, but this is v1 times delta t. And then we have the acceleration, which points straight downwards. It's 1/2 the acceleration times delta t squared for our kinematic equation here. And my equation says if I add the v1 delta t vector to the 1/2 a times delta t squared vector, I get delta r. So if I place these two vectors tip to tail, the resultant vector is delta r. Okay, so now let me redraw this down here. So I have v1 times delta t at an angle of 40 degrees. I have my delta r vector, and I have my 1/2 a times delta t squared vector. Okay, now we saw how to find the x component of the velocity. Now we're going to do something similar to get this distance. That's going to be the x component of v1 times delta t. So this is v1 times delta t times cosine of 40 degrees. That's going, if you make a right triangle, here, that would be this side of the right triangle. But you have another right triangle like this, where the hypotenuse is delta r. And I don't know what this angle is, but I do know that this leg of the triangle would be the x component of the delta r vector, so this is also equal to delta r x. So now I have, well, if r1x is equal to 0, delta rx is equal to r2x. So I can say r2x is equal to v1 times delta t times cosine of 40 degrees. Now if I go back to my equations here, I can compare this to my position kinematic equation, where I have just the x components here. So delta rx, that's equal to r2x, since r1x is equal to 0. v1x is v1 times cosine of 40 degrees. So the v1 and the cosine of 40 degrees, that's v1x times delta t, so that's what I have here, plus 1/2 ax times delta t squared, but ax is equal to 0. So this, which we got from our triangle, is the same as the equation that we have for the x component of the position kinematic equation. Okay, and now we're going to take this same vector diagram and we're going to look in the vertical direction. So if I take this smaller right triangle, this side of the right triangle would be delta r y. And from here to here, that's 1/2 acceleration times delta t squared. We said the acceleration was equal to g. I'm looking at the lengths here, so I want everything to be positive. So I'm going to say delta ry, that goes from here to here. Then I'm going to add to that 1/2 times the acceleration times delta t squared. So that's this distance plus this distance, so that entire distance, that would be from here to here if I add these two pieces together. Now if I look at this larger right triangle, where v1 times delta t is the hypotenuse, if I do the sine component, that's going from here to here. So just like we did v1 delta t times cosine of 40 degrees to get this distance, this would be v1 times delta t times sine of 40 degrees, and that's the entire distance, so these two small pieces added together make up that v1 times delta t times sine of 40 degrees. Now let's compare that to what we would have if we use the position kinematic equation for the y components. So I have delta ry on this side of the equation, which means I'd have to move this over to the other side, and over on the other side it would be negative. And if up is positive, ay would be negative g. So if this is on the other side, that agrees with what we have here. And then this term, we have the v1 and the sine of 40 degrees, that's v1y. So this is v1y times delta t, so that agrees with what we have here. So you can either get these two equations from the vector diagram, or you can use these equations instead. Okay. So after I have that, I need to fill out the table completely. Okay, so I need to find everything. Right now I have two equations, and I actually know what delta ry is. So we said before that's 1 meter, or you could say 1 meter minus 0. That's also 1 meter. So this is 1 meter plus half of 9.8. That's 4.9 meters per second squared, times delta t squared. We know v1 is 15 meters per second, so v1, actually we can do this. So I had v1x and v1y here, which I'm going to need to find for the table. So if you plug that in your calculator, for v1x you should get 11.5. So this is 11.5 meters per second, and for v1y we get 9.64 meters per second, and we can put that in the table also. 11.5 meters per second, and 9.64 meters per second. Okay, now here I could plug in the 15 for V1 to find, well, to simplify this. Or I know V1 times sine of 40 degrees is 9.64, so let's just call this 9.64 meters per second, then times delta t. Okay, now, here I have a delta t squared in this term, a delta t in this term, and no delta t in that term, which means in order to solve delta t, we're going to have to use the quadratic equation. So I can bring this over to the other side, and for the quadratic equation, it should have the form ax squared plus bx plus c is equal to 0. Instead of x, we're going to have delta t, so I'm going to put the 4.9, I'm going to take the units out now. So this is 4.9 times delta t squared minus, if I bring this over to the other side, 9.64 times delta t plus the 1 is equal to 0. Then using the quadratic formula, I have delta t is equal to 9.64 plus or minus the square root of 9.64 squared minus 4 times 4.9 times 1 divided by 2 times 4.9. That would be 9.8. We get two solutions for this. So one solution is 0.11 seconds, and the other solution is 1.857 seconds. Both of these solutions are positive. We have to figure out which solution is correct. When the human cannonball is launched, the human cannonball goes up and then lands. This is 1 meter above where we started. But there are 2 points in time at which the human cannonball is 1 meter above where they started. So this would be the first solution, and that happens soon after the human cannonball is launched. So at 0.11 seconds, we are 1 meter above where we launched from, but we want the solution which is on the way back down. So that would be the 1.857 seconds. So both solutions mean something, and we have to figure out what they mean in order to pick the correct solution here. Okay, so we want the 1.857 because if the human cannonball is going to land in the net, they should be on the way back down when they hit the net. And so we can put the we can round it when we put it in our table and call this 1.86 seconds. And now I want to know R2x. So I can go back to my equation here, plug in delta t, and I get R2x is equal to V1 times cosine of 40 degrees, that's 11.5. So this is 11.5 meters per second times delta t, which is 1.857 seconds. And that gives me for R2x about 21.3 meters. Okay, now I have to find v2x and v2y. Well, I have my velocity kinematic equations, which I can use here. For v2x, it's easy because ax is equal to 0. So if ax is equal to 0, v2x is equal to v1x. So v2x is 11.5 meters per second, and you don't have to show any work for that. And then finally, usually the last step in all of these problems is going to be to use this equation to find v2y. So I have v2y is equal to v1y plus ay times delta t. v1y is positive. The acceleration is negative 9.8 meters per second squared. Multiply that by delta t, which is 1.857 8.57 seconds, and you get for V2y roughly minus 8.55 meters per second. And we can put that in the table here, minus 8.55 meters per second, and then we're done.